This conference will now be recorded.
Thank you, Rochelle. Please take note that this conference call is being recorded. Should you have any objections to that, please let us know by unmuting yourself and letting us know now. Good. Good afternoon, everybody. My name is Heidi Snyman. I am the Vice Chairperson of NICOLA, and it really is a pleasure to welcome you to our webinar series and specifically to today's webinar. So I would like to start off with a bit of a care share or a health and safety share. And I was thinking of one that combines both health and caring, which is the recent retraction of quite a millions of cans of vegetables, baked beans, corn, and cream corn, and things like that from two major production companies in South Africa, Hugo and Koo. And so I've heard of quite a few people that found some of these products in their cupboard. And just to note that it's from June 2019 up to now. That batch, there's apparently some of the tins that the integrity is not quite what it should be. And I was speaking to quite a few people that said they're simply just going to throw them away. And that's actually not the right thing to do, because in South Africa, we have people that salvage on landfill sites, and that will, see that as food, and then your good deed of getting rid of a defunct product, it might not have been the right thing because somebody else will consume it. It might not have the insight to know that that's part of the batch that's been retracted. So if you don't want to take it to the supplier where you bought it, please open the tin, discard the content, and then throw the tin away. Or otherwise, the right thing to do is to take it to either where you bought it or one of the other supermarkets that sell it, and they will then make sure that it gets to the proper supplier and be discarded. Okay, so a little bit of an introduction to NICOLA. I firmly believe that when you hear something 20 times, then it becomes ingrained, and so it's lovely to introduce you guys again to NICOLA. We are a professional member association, and we provide knowledge sharing and dissemination opportunities through working groups on relevant topics, contaminated land training, and then our annual conference. And we are going to spend 2 minutes to explain to you what our next conference is about, the SUSTREM, which is an international conference this year. Then we give networking opportunities such as the webinars that we're all part of now, regular evening networking events, which with COVID is obviously not happening at the moment, and then industry forum events. And then we're trying to inspire and aspire to be relevant locally, but internationally at an acceptable level, by stimulating coordinated interdisciplinary projects on collaboration and looking at problem-orientated research and outcome research or impact research. We were awarded by the DFFE in 2019 the waste scorer for our contribution on land remediation, which is a wonderful feather in our cap, because it means that as a society we have a voice with the regulator. The next slide, please. And so I'm very excited to just again say the early birds registration is still another day or two, so it's actually tomorrow. So please try and register for it. It'll take place 3 to 5 November. It's the 6th SUSDREAM conference. It's been all over the world, and now for the first time on the African continent. And so there's lovely opportunities on the 3rd of November. There is career development opportunities, and the 4th and the 5th is the conference. Please make use of your snipping tool to just maybe snip the website, and please visit it and look at it. Very exciting. I'm really proud of that program that we've managed to put together. Excellent speakers. So please make use of that. And without further ado, I'd like to introduce our speaker of today, Bill Brab, who is a senior remediation geologist at AST Environmental. He's got 18 years of experience in environmental geology and remediation. He started at AST in 2011 and have developed AST to become a leading in situ technology company, providing unique injection approach, which we'll hear about today, developing conceptual site models, integrate designs and injection techniques. Bill graduated from the University of Kentucky in 2001 and holds a bachelor's degree in geology, and he is a professional geologist registered and licensed to practice in Kentucky, Tennessee, and Alabama. Without further ado, Bill, the floor is yours.
Wonderful. Thank you for the introduction. Am I coming through loud and clear this morning?
Very clear. Thank you, Bill.
Great. Okay. So we've got the nice fish desktop image here, and we'll pull the presentation up in front of us. We should have that on the screen now. If everything's confirmed, I will begin. So thank you, everybody. Appreciate you taking the time to attend the presentation today and hear what I have to say and participating in this program. I know I'm probably going to pronounce it wrong, but Salabwana. Appreciate being given the opportunity to be here. As the introduction indicates, I'm located domestically here in the United States of America, based out of central Kentucky. Where our base of operations for AST Environmental takes place. I want to talk about an actual case study here. It's one of our longer case studies for a petroleum release site. This is a presentation on this in situ LNAPL remediation of a rupture at a pipeline transmission facility for conveying petroleum products here within the domestic U.S. So a little bit of site background on the facility. The geology is located in the Thumb and Upland physiographic region of Michigan Lower Peninsula. The overburden materials is predominantly sand and gravel, varying anywhere from 8 feet to 22 feet thickness. Sorry for no metric conversion here. Hopefully this transfers well. The actual consolidated unit directly beneath that overburden is the Saginaw Formation, which generally comprised of sandstone and shale. The occurrence of groundwater occurs anywhere from 9 feet below grade to 14 foot below grade. You have both a unconsolidated sediment aquifer. You also have a bedrock aquifer. And the groundwater analytical data from the release out here does indicate that there is a hydraulic connection between these two distinctly different geologic units. So again, the pipeline transmission facility is located in southern Michigan. It's kind of on the northern primary boundaries of the domestic United States here, up in the Great Lakes region. Approximately 1,700 barrels of gasoline fuel was reported released in June 2000 following the failure of a 16-inch stopple fitting. Approximately 1,400 barrels were estimated to be recovered during the initial response. That's from surface vacuuming, excavation of soil, boom recoveries, things like that. About 30,000 tons of impacted soil was removed and disposed of at a properly permitted landfill. and groundwater extraction system capable of up to about 25,000 gallons per month operated until 2012. And essentially, at the time that this came to us, quarterly groundwater monitoring had been conducted to the present time, which we became involved in the first quarter of 2013. So that's when we started working on this project. And so, looking at the initial conceptual site model for this facility, we'll first look at soil. So, looking at the site plan on the left-hand side, we have your benzene isoconcentrations and the indication from the orangish, reddish orbs that we see where there's indications of NAPL in the samples present. The soil samples indicated soil mass begins around approximately 4 feet to 5 foot below grade and extends below the groundwater table. The soil borings indicated elevated PID readings in the saturated soil, but because of sampling guidelines and requirements based on the state of Michigan, no saturated soil was collected or delineated below the water table itself. So this indicated a significant gap that may be present in the data package that was provided initially. Moving on to the actual groundwater conceptual site model, we could see a slightly different elongated plume that we see from the source indicated by the yellow orb where the LNAPL is actually occurring in the monitoring wells. We have approximately 380 foot long elongated plume that extends to the northeast. And the groundwater impacts were primarily located within the unconsolidated sediments overlying the bedrock. We did have persistent LNAPL present in certain on-site monitoring wells. And again, I referenced that indication of connection between the overburden and consolidated bedrock unit. We do have low-level dissolved phase constituents present here in monitoring well 24D at the distal end of the plume. This is the furthest point out with any detections, and that well itself is in fact screened within that sandstone and shale bedrock. So we do have contamination that's actually being realized once we get very far down gradient at that distal point in 2013. And so the regulatory body, the Michigan Department of Environmental Quality, requested an updated remedial action plan to try and see some sort of resolution for this site. So at the time that we became involved and were asked to evaluate this, there had really been no specified soil remediation goal. But they did want to see a significant reduction in groundwater contaminant concern concentration, and obviously the elimination of any measurable LNAPL within site monitoring wells. My company, ASP, was contracted in early 2013 to provide a remedial option for consideration. And this option included a preliminary remediation design based on the existing CSM just for budgeting purposes and a rough order of magnitude estimate of scale of work. This also included what we call the remedial design characterization. I'll talk a little bit more about that in just a second. That preliminary design and plan included a pilot scale injection of the trap and treat BOS 200 and a full scale injection of the trap and treat BOS 200. I believe I go into detail in a future slide of what that material is. If you're not familiar with it, we'll work our way there in just a second. So the roadmap to success on any remedial approach, and if you've ever seen a presentation by AST or RTI, you'll see this flow chart or this diagram come up frequently. And so what you essentially just have is a treatment train or whatever you want to call it, or a step-by-step process to get from beginning to end of this remedial goal. And so essentially, I've already talked about the initial conceptual site model review and preliminary design, and I referenced this remedial design characterization, or RDC as we call it. And what this essentially is a investigative effort to go out and fill data gaps that are present within the existing conceptual site model. We want to try and get higher resolution data to be able to more effectively and surgically design a treatment amendment for a specific facility based on the actual contaminant mass present at the site and how it varies with depth and spatial differential between the site location based on where you are on the property. And so taking all that data from the RDC, we come back in and update that conceptual site model to have a more, what we believe is accurate picture of the actual fate and transport of the contaminant in subsurface at the facility. we can then take that information and update the preliminary design and redesign it to be more effective and have more confident end result predictions for performance at the facility. So then once that's approved, we go to actually implementing the technology, whatever that may be. And then, of course, you want to have some level of performance monitoring to see, if what you did happened and if it's working, or if we need to kind of step back and maybe recycle some of this information here and work our way back through. In this facility here, we'll see after we pass the next slide or two, did require multiple trips to the site because of the amount of contaminant mass present. So what we can see from this model here is that we, by prediction, based on the information available and what we know of the site, we do have to kind of step back through this process in order to get to the end goal of the facility. And so I mentioned the BOS technology, specifically in this case, BOS 200 here in the middle bottom section. We do have a chlorinated solvent component treatment that we have available to us. We have BOS 100, which is an activated carbon impregnated with metallic iron. It's a granular carbon, so a larger particle size. This is strictly looking at an abiotic beta pathway elimination degradation pathway. The project has extensive longevity within the subsurface, 7+ years, but theoretically 7+ years demonstrated from both lab studies and field studies. But theoretically, we can go to 10+ years based on the availability of iron and contaminant present. We do have some background noise, so if you are unmuted, please mute your mic so we're not having some background noise here. The improvement on the BOS 100 is what we call CAT 100. And so this was developed for sites where BOS 100 was to be limited based on the actual iron present. So when you get into your heavily impacted CVOC, DNAPL type scenarios and mixed recalcitrant COC sites. Essentially what we've done is we've taken the BOS 100, the granular activated carbon impregnated, again, which is an interesting product because the material is bonded to the carbon surface. It's not just carbon and iron floating around in a mixture. These are actually bonded components that are truly a unique compound. But the CAT 100 takes this BOS 100 and we add an electron donor source in the form of starch or chitin, and then we add a yeast extract and a consortium of bacteria. That bacteria is specifically designed one set to degrade the complex carbohydrate to provide simple sugars and free electrons for shuttling across the electron or the carbon surface. And then there's another set of bacteria that's present with the purpose of helping to degrade some of the chlorinated compounds. BOS 200, as I mentioned, which was used on this particular facility we're looking at today. This is primarily used to treat petroleum hydrocarbons. It's a powdered activated carbon mixed with terminal electron acceptors in the form of sulfate and nitrate and background micronutrients, plus a consortium of facultative bacteria that take advantage of aerobic and anaerobic processes. Recent improvement to this product for, again, heavier contaminated sites where NAPL and high concentration exists is to take some of the information that came out of the CAT edge studies, and again, adding an electron donor plus a yeast extract and another set of bacteria that helps to kind of facilitate that breakdown of starch and work with this consortium of bacteria here. This particular site, because of the contamination here, we probably would have used BOS 200 plus if it was available at the time, but this was a recent development and implementation here within the last couple of years. So unfortunately, it was not available at the time of implementation at this facility in particular. And so looking at the remedial design characterization, I mentioned this data gap filling analysis that we implement in order to try and update this conceptual site model and get a better snapshot. And these are fairly aggressive, high density investigations that provide a substantial amount of information about what's going on at the facility. And so if we look here at the site map on the left-hand side, this is the transmission facility here behind the fence that we can see at the very bottom of the site plan. This is a confidential site, so I do have to kind of sanitize a little bit of the information as to where it's at and what the facility looks like. But what we can share is the how the pipelines or the pipes come out of the facility and go to the next facility in the terminal sequence that they have. And so we have a main pipeline that runs out here and another one that goes here, and these cross. This one here, I believe, goes underneath the one going straight up and down. and then these turns left and goes up the road. And then these two pipelines here are in parallel and lay on top of this one that goes beneath it. All of the purple points you see here are the RDC points indicated here by this set of bullets. We installed 34 soil borings going from ground surface to bedrock interface. And these are continuously sampled every 2 feet and submitted for analysis. RPI, the intellectual property owner of the trap and treat products, has a full service environmental laboratory located in Golden, Colorado. And we can send them as many samples as we need that are analyzed and sampled and no cost to the project. It's a pro bono service that's built into the business model of RPI. And they can provide VOC analysis using method 8260B. So we can look at both the speciated VOC constituents, plus we can also look at the total volatile hydrocarbons. So looking at that total mass fraction that is present within that petroleum release that's located in the subsurface facility. Of those 34 locations that we installed borings, we also installed a nested well pair, essentially looking at a discrete interval for vertical delineation of groundwater. So we had a screened interval looking at the deep portion of that borehole, roughly looking at from bedrock surface to about 4 feet above bedrock surface. And then that shallow interval was set above that with a minor bentonite seal in between to try and isolate 2 distinct groundwater bearing zones. Those groundwater samples were also analyzed for that VOC 8260 method, but then also looking at anion 300.1. I referenced that we add thermal electron acceptors to the BOS 200. So that anions analysis, both on the baseline and on the follow-up analysis, is quite important for looking at the degradation patterns of those materials as well. And again, as I mentioned before, that RPI analysis of great benefit to these projects is that it's provided at no cost. So a significant portion of a lot of these investigative costs do come in fact from the lab analysis from a commercial laboratory. So looking at the data following this remedial design characterization, going back to the environmental the regulatory body that's overseeing this particular facility, they did establish a soil and groundwater standard more specifically to be defined for this remedial approach. And the soil standard was established at 10 ppb for benzene. Groundwater was established at the MCL of 5 ppb for benzene. And so the benefit of the CSM that really came out of looking at, or the benefit of the RDC coming out of doing this and updates to the CSM showed us some very interesting data. So there was the pilot study I mentioned before, so that's that first event. The amount of material required to address what we assumed in the pilot study would have been about 20% shy. Not a big deal, but still, you know, we weren't quite hitting the mark. But what we found based on the amount of contaminant mass actually still present within the subsurface was that the second event was not even going to come close to being able to address the issues. And I can show you here this purplish magenta line that's overlaid on the map is showing the preliminary budgetary injection design plan that was given based on the initial information. We had a barrier type approach here located directly at the fence line with 2 kind of areas in between to evaluate based on these areas of known soil versus groundwater contamination. And what we found was that, you know, one of the things that we harp on all the time is that there was significant soil mass present across the unsaturated and the saturated intervals. And so one of these big pieces, one of these components that is typically disregarded because either of a sampling guidance or procedure or, you know, the regulatory goals for the actual soil cleanup standard is elevated. This is typically disregarded and left out of the equation, but does in fact provide a significant contribution to the total mass in the subsurface. And so based on this new information, we were able to provide more of a surgical approach. So you can see this figure here is fairly generic. We have 1 area, 2 areas, and then this kind of distal area here that's just kind of globally capturing a fairly large footprint across this facility. So this surgical approach came out of doing this RDC, where we were actually able to design each area based on each individual RDC sample location. And so at each of these locations, the injection loadings varied with depth based on the actual mass present and its distribution across that specific zone. And just an example of showing this variability within the subsurface, right? So again, we talk about, you know, most guidance documents or most beliefs are that, you know, if you have an LNAPL specifically, you don't have mass below the water table. However, we've seen time and time again that if you have a significant head driving that contamination, it will go below the water table. And so this is very important, why it's crucial when you're dealing with, especially with LNAPL sites, that you do get saturated soil data, both speciated and total mass fraction. And so 2 points, I'll back up one slide just to kind of give you a visual of where this is. RDC 11 and 12, this is in your source area, so we're talking about source mass here. So looking at concentration versus depth, RDC 11, RDC 12, these are 2 different borings side by side. We also have, looking at concentration over the top, benzene is reported in ppb, whereas PBPH is reported in ppm, so just adjust your eyes for that. The blue line is benzene in soil, the orange line is PBPH in ground, or PBPH in soil. Water table overlaid for you to get an idea of where that's located. And then we have these bars here located on the left-hand side of each plot. These are the discrete intervals of the screen interval where we took a water sample from. So we're looking at benzene and groundwater specifically on both of these. And what we can see from both of these borings is that we do have a significant, at least on RDC 11, we do have a significant mass contribution above the water table. However, we do see significant mass is in fact located below the water table. We do have a concentration gradient showing that we do have higher concentration benzene in the shallower zone, but we do see probably about a 40 to 50% total 40 to 50% of what we see in the shallow zone is present in the deeper zone as well. So we do see a gradient across that. Similar pattern over here, except the main difference is that with RDC 12, our highest soil contribution is either at the water table or just below it. So again, if we were to go out here and design based strictly on groundwater and shallow soil concentrations, we'd miss a very large picture here looking at this benzene concentration. I mean, this is no small number. It's the hottest sample on site, somewhere around 98 ppm. So very significant amount of contamination below the water table, both fueling NAPL and sustained persistent dissolved phase concentrations in the wells present at the facility. And again, we can see that this groundwater concentration, note the difference of the scales on here, is pretty significant within this area, looking at 20 ppm, almost 20 ppm of benzene in that shallow zone. So again, I talked about a surgical design based on each injection point. This table to the right is fairly busy. Don't focus too heavily on it. The main point I just wanted to show here is how we carve this specific area up, both based on the area reflective of the individual RDC point that it's designed, but then also the variation of the dosing of the BOS 200 with depth. So it's quite valuable, again, to be able to have this high density soil and groundwater sampling, because we do have the power to be able to do this and to be more surgical and efficient with the placement of the product. And again, here's just the variability. I'm showing the overlay of the original assumed plan based on the pre-RDC conceptual site model, but then this colored variation of each individual area that's depicted on the right-hand side by the tabular form of how we actually carve the site up and implement this technology to be deployed in the field during full-scale remediation. And a little bit of talking about the actual methodology. BOS 200, as I talked about, is a powdered activated carbon mixed with other solid amendments that are partially soluble. So we're actually injecting slurries here. So there are some best practices to installing slurries in overburden settings. Nice little schematic on the left-hand side showing temporary dedicated direct push points that are installed but then abandoned after the installation. Again, these slurries are installed using a high flow rate and relatively small injection volumes. We're putting a very dense injection grid in place. We have placed this material into the formation through the injection of these high pressure bursts of material. We do that in a top-down fashion where the path of least resistance is in the horizontal versus the vertical. Again, these are dedicated temporary points, and the rows that we install are perpendicular to groundwater flows. So we can see a completed borehole here with an individual interval shown here and here. These are typically offset by about 2 feet. And then we can see from the adjacent location, oh, by the way, once we get finished, we seal the hole with bentonite so that it seals the hole up. The adjacent point, both going down the line, if we were to picture the row of points going from left to right here, these would vary and stagger off of this 2-foot spacing. These would be like odd intervals, and these would be even intervals. But you can also envision both coming out of the screen at you and going into the screen away from you, that this is varying with the adjacent points in the rows with it. And so what you ended up having is you have this interconnected lattice work of tortuous pathway for groundwater to move through that at some point it has to intersect one of these injection intervals. So it's trying to get a fairly dense installation of this material. So just a visual representation photograph of the site. Here's your pipeline facility up here behind the fence line. These are the actual above grade pieces of infrastructure as part of the metering process and the switch station that goes on at this facility. Your injection projects out here. This stick-up well and this stick-up well, these are your 2 locations where persistent LNAPL was present during the initial CSM. And then this marker here and this marker here gives an indication. Oh, we've got another one right over here by the product. Gives an indication of the pathway of the underground pipelines present out here. This is the injection unit right here on this trailer, water truck to supply that, and the palletized material delivered to the site for installation. And again, there's that typical geoprobe for the direct push installation that most people are used to seeing. So following the implementation of the first injection event, I mentioned that kind of flow chart earlier in the presentation, that sometimes you need to repeat this in order to get a better picture of what's actually going on the site. So we did a first round injection in 2014 is when it was implemented. And we came back 1 year after that was implemented and did a second RDC so that we could see performance of the soil reduction and get a snapshot to update our baseline for tweaking the second injection event that was planned. And so we did 12 soil borings completed adjacent to some of the key locations identified from the 2013 RDC within the treatment area. We also did some groundwater grab samples from these resample boring locations just for adjacent comparison to get the total sorbed and dissolved phase mass comparison. But we also took the opportunity to look at these soil borings for a visual inspection of the BOS 200 itself to see how it was distributed within the subsurface. Again, that laboratory analysis that RPI was performed at no cost, and that was used to establish a new baseline for that second injection design update. And we also looked at that to try and just get an eyeball estimation of total mass removed to date following the first injection event. And so based on some of those limited, I'm using that term quite boldly here, that we can only look at a small snapshot. 12 points over that entire treatment area is not a lot of points. But from that limited data, we saw an up to 85% reduction in benzene in some areas in the soil, looking at a 68% reduction in the TVPH, that's the total contaminant mass, which when you're removing LNAPL, that's the most important. But then we look at groundwater, we see some similar numbers as well, 73% reduction in benzene. Again, these are the higher numbers I'm picking here, an 88% reduction in TVPH. So a full-scale second event was approved and implemented in 2016, and both the consultant and the client that was actually paying for this, and this is in fact an insurance covered release for the pipeline transmission, this facility itself, they opted to go ahead and do a third event to try and expedite that closure, which we implemented in August 2018. So we aren't going to be monitoring for as long as it was predicted to be evaluated following the implementation of these technologies. So I just wanted to highlight some data before we step into some of the kind of closing arguments or the closing pieces of information of performance at the site. Is that second RDC result, looking at, okay, some of that performance that we saw in the degradation. This is some very interesting data. I'm just showing here RDC11, if you can kind of remember where that was on the map, kind of the central part between the pipelines. Again, we're looking at RDC11 and RDC12 here. RDC12 is on the next slide. But if we look here, what we can see on the left-hand side is this left-hand plot is the benzene plot that we saw before, and this is the TDPH plot here, looking at soil data. I've overlaid, again, the water table and the injection interval for installation. And so what we see here is even in the unsaturated zone, we see a significant knockdown of that benzene concentration. And then once we get into saturated conditions, we see some additional higher rates of performance as well, because we're constantly saturated within that zone. Get a little bit of distortion here at the water table, and that's probably just due to distribution, where we change the dynamic of the interface. Similarly with our TDPH, we can see that at this shallow interval outside of treatment in unsaturated zone, these are the green is post, but we didn't create mass here, so this number is probably very similar. So there's really no change, right? But once we get into the actual zone of treatment, we can see a knockdown where we started injection. Again, that kind of blurring, maybe some distortion based on the interface with the water table here. Then once we get down into the actual saturated zone, we see some pretty significant performance and reduction in this zone as well. And we see this last data point here is fairly close together, but it is low concentration. So if there's less mass present, there's less mass to degrade. So our actual removal rate is a little bit slower, just because there's less availability of that food source for the petroleum degrading bacteria that's on the carbon surface. RDC12 right next to this, again, here's that really significant peak on benzene that we have below the water table. And we could see a significant knockdown of that after we get into the saturated zone and actual treatment present. Again, we get that kind of similar concentration that we see over here of TDPH. Again, I think this is just a distribution issue at this interval, probably just that variability in sampling too, because we can't quite get to the exact same spot because there's a well there. But then again, looking below that water table, once we get at that high concentration, this concentration here, ppm is fairly significant, indicating that we actually have NAPL at that location. We do see a significant knockdown. And again, kind of that similar concentration as we get lower concentrations with depth. So quite well, we were very happy with the way that this was both distributed and what we saw in the post results of the second RDC. And looking at groundwater here, we do have extensive groundwater data on the site quarterly up until a point where they switched to semi-annual. This is looking at all three injection events, looking at just RDC12D. So we're looking at the deep fraction of this RDC point. And the main piece I want to illustrate here for everyone to see is what
Colleagues, am I the only one that's lost Bill?
Can you hear me still, or did I lose audio?
We can hear you, Bill, and we can see your presentation.
Can you hear me? I lost audio for a second.
Yes, we can hear you.
I lost audio for a second.
Can you hear me? I lost audio on my headset.
Bill, we can hear you.
Can you hear me now? I lost audio on my headset.
Yes, we can hear you.
Okay. Sorry, I just had to switch to my microphone and my speakers on my computer. I apologize for that. My headset kicked me off. So hopefully you can still hear me okay, and it's not distorted in any way, but I'll continue on microphone.
Yes.
So, okay, so I'll continue. I was talking about the pattern of carbon absorption versus biodegradation is what I wanted to highlight on this slide. What we have essentially is looking at just this blue line being the benzene concentration. We have orange line is sulfate. Okay, so we added a thermal electron acceptor to the mixture, and we track that in parallel with the contaminant degradation. So the microbes, the dominant degradation process of BOS 200 sits within sulfate reduction with a little bit of fermentation and methanogenesis, but primarily sulfate reduction once it kicks off and it really gets into full swing. So we track sulfate primarily as the parallel thermal electron acceptor for performance monitoring. And then I've overlaid here, as you can see by the dashed lines, these are the individual injection events. This is the event that occurred in 2014, 2016, and then the final injection event occurred in 2018. And so the pattern that you typically will see with the injection of carbon substrate for degradation like this is you'll have a high concentration with an immediate mass removal where this is stripping the mass from the groundwater. And so looking strictly at benzene, we'll see that mass plummet to the end of the first injection event. But then what will happen is we've offset the equilibrium within the subsurface and the equilibrium between the sorb phase and the dissolve phase. And so what happens is you'll have what the industry typically will call rebound. We don't like that term because this is an interim concentration goal that we can predict. So I expect to see this number, but what the big important part to see is the comparison between this number and this number. This is a significantly lower concentration that we see from what the initial concentrations were prior to injection. That stabilization concentration, then once we get the actual biological degradation, which takes a couple of months to really kick in, begins to drop off at a linear kinetic rate. And so again, I talk about this addition of sulfate. We can see the increase in sulfate after injection. So we've augmented the system and added the thermal electron acceptor for bioavailability for this degradation process. And we see that material degrade with time in parallel to the contaminant present within the subsurface. And again, we know that there's significant mass out here. So again, we can see that concentration plummet right after the injection, but then that new concentration is lower than where it was prior to injection. And that carries on with time as well. Again, we see this huge jump in sulfate because we've added more sulfate and it's more readily available to augment what was present here prior to. Then this third event, we see a little blip up because we probably liberated a little bit of mass that was still kind of clinging to the soil based on just the energy of injecting at high pressure and high flow. But then we see that taper off very quickly to the current monitoring event where it's hovering very close to that MCL. So just looking at the patterns here using the groundwater as the metric for measuring performance at the facility. So to kind of wrap up our presentation, the pieces that I put together here is a comparison visually on the left-hand side. We can see looking at our benzene isoconcentrations in groundwater and the occurrence of LNAPL in that central zone, but then also a calculation looking strictly at groundwater because we can't go out and sample soil every quarter. That would be way too expensive for the client to do, and most people don't want you poking holes around pipelines very often. So using groundwater as the indicator for performance, what we've done is looked at those benzene isoconcentrations and looked at the relative max concentration of what that isoconcentration represents, the average concentration within that, the area that represents, the thickness of water, porosity, looking at that in liters, and then getting into an actual total mass of benzene within groundwater. So we'll kind of walk through each of these subsequent slides. It's going to show the same thing. It's just going to change based on monitoring period. So what we have here is time equals 0, groundwater sampling prior to the first injection event implemented in April 2014. Again, we've seen this figure early on before. We have that distal bedrock well showing concentration of benzene. The treatment area is all the way back here. So what's really important is to keep that in mind as you see these subsequent benzene isoconcentration maps. So we see immediately after injection, roughly at 6 months. So looking at the seasonal colder months here, we see a significant attrition and reduction in that extent of that benzene groundwater plume. We also see a significant mass reduction, right? We started at 5.9, we're now at 2.1 total mass pounds of benzene, right? But what's really important to see is that we have right at the MCL detection, just above it in monitoring well 24D here. And so as we continue on forward, just kind of just picture all these different shapes and aerial extent, as well as the relative orders of magnitude concentration in these wells. We see, within less than 1 year, we see non-detect concentrations show up in that bedrock well. So we've cut off the source that was being realized within that well in the bedrock further down gradient. We also see that we're bringing any overburden mass closer and closer to that defined property line. So we're looking right now at the second RDC. This is 1 year post-injection, or a little bit greater than 1 year post-injection. Again, looking at the mass dropping, we're at 1.81 pounds of benzene. So now we're at 18 months, December 2015, looking at 18 months post first injection. Kind of stable on that plume, but again, we plan on having to do a second injection of that event out here because of the total mass present. We can't get there in one event, right? So this is time equals 0, immediately prior to that second injection event in April 2016. We can see the plume is fairly stabilized within the area of the actual treatment, and all distal concentrations are either non-detect or below or approaching the MCL. Looking at that power of the carbon, the instant reduction, significant reduction in total contaminant mass. We do have a couple blips of NICOLA. These are adjacent to the pipeline. Keep in mind, we're obviously limited. We can't inject in the pipeline itself, so we do have a sustained source that remains ever present from the geology that's adjacent to the pipeline, and we were specifically limited on proximity to that, so we know we can't get treatment amendment up into that area, so we have to essentially try and account for the back diffusion or the bleeding off of mass that's continuing to hemorrhage out of that material around the pipeline itself. So looking at June 2017, further stabilization, we see the NICOLA disappear for a while, approaching that 1 pound of benzene contaminant mass. Now we're below the benzene, the 1 pound of benzene total contaminant mass. We do have a little blip of NICOLA in 26R. That's location is right where the two pipelines cross. So we got a little bit of a hydraulic trap there, so to speak. So we see NICOLA will tend to sporadically collect in that area or within the source as time goes on. Maintaining still, again, below that 1 pound benzene total contaminant mass or speciated mass at the facility in March 2018. This is right before we move forward with the third injection event. Again, that little blip of NICOLA showing up in 26R. Looking at May 2018, a great reduction in mass here, only looking at 0.35 pounds of benzene. Again, just that little sheen of NICOLA showing up in 26R. Here we're at the baseline right before the injection event, number 3 in August of 2018. Again, everything's coming into the property lines and staying on site at this point, with just that little bit of NICOLA showing up again at that kind of distal point. Again, looking at the visual here, quite profound. Again, that power of that absorption of the carbon immediately following that injection. We see a significant benzene reduction just from carbon absorption alone, stripping from the groundwater. Here, a little bit of dynamic change following that event. We're looking at 1 quarter post-injection. We do have NICOLA showing back up in 11R and at RDC 22, which is located kind of right at the property boundary there on the kind of northwest side. But it's also adjacent to a pipeline, so it's probably seeing a little bit of mass coming out of that backfill around the pipeline itself. March 2019, things kind of stabilized a little bit more. We do get back over that 1 pound of benzene mass for a short time, I believe, here, but we do see that NICOLA has not returned at this point. Moving into June 2019, the regulatory body MDEC or MDEQ has decreased the sample frequency to semi-annual instead of quarterly at this point. Again, we're looking at mass again approaching that 1 pound benzene mark. Again, we do get a little bit of a blip of NICOLA showing up in 2019. Again, it's just showing up as a minor sheen, but it is detectable and measurable. So just have to kind of keep an eye on that. But these are those two RDC points that I identified earlier from both the RDC and identifying as the high mass zones that are present within that source area. So again, here we're now below the 1 pound. We're looking at June last year, so we're rapidly approaching the end of the sampling period that I have available to show to you. We are below that 1 pound of benzene, doing quite well on the total, or on the speciated mass measurement that's being measured with time for performance. Then looking at December of last year, there is a current data set at the lab that I don't have available to me just quite yet. We'll be reporting on that update once we get the data from them. But we can see again, just that little sheen shows up in 26R and 11R. The client did go out here and replace 12R and 11R because these were small diameter wells, and they believe that there may just be some LNAPL mass bound up in the filter pack itself. And so the idea is that putting in a new well and getting a true, larger diameter PVC construction may be the way to actually get a better representation of what's going on here in this subsurface and adjusting the screen interval. So what we see here is just that little sheen of NAPL, but again, we're at that lower limit of benzene mass. I do know from the most recent gauging event or sampling event that occurred in May that there was not any NAPL measured in the new wells after installation. So fingers crossed, one of the goals out here is to eliminate the NAPL. And so once we see that go away, they can move forward with dialogue for a risk-based closure at the facility. But now we're just looking at a snapshot of those numerical tables, looking at that initial event that I showed before of April 14 versus the most recent in December 2020. We can see that significant reduction between 5.9 and 0.45, and that mass matches the 92% total reduction that was indicated from some of the data from early sampling at this facility, or the follow-up sampling at the facility. And then we've got a graphical representation showing that total mass with time, looking at that benzene mass in groundwater, each injection event overlaid here with time, and that linear rate of decay, if you were to plot this out, would be fairly obvious from this graph here. So site's doing quite well, the client's happy, the consultant's happy, we're happy with it, and one of the benefits of it is because of the nature of the site, we're permitted to monitor this for a very long time and show the efficacy of this product and how well it works in a sustained long-term setting. And with that, I really thank you for taking the time to hear my presentation. I apologize for the audio issues there late in the talk, but fortunately we were able to switch over and get to where I was audible yet again. I do want to just put a plug in for some of our other presentations if you have never sat in on them. We do have a webinar archive at our website here located on the screen. And then of course, if you want to reach out to me for any questions directly that can be more detailed offline, feel free to do so at my email address here located on the screen. And with that, I will end my portion of the talk. If anybody has questions, I will take those now, or we can work our way towards adjournment.
Thank you, Bill. Rochelle is just going to put a slide up. Colleagues, in order for you to get your CPD points, there is on the screen now a password, SUSREM, which you need to just jot down in order to qualify for your CPD points. Please just jot that down at this stage. Thank you. In terms of questions, we have one question so far, which asks, it's Haley Thomas that's asking, how effective is the BOS in the unsaturated zone?
Yeah, that's a great question. It is effective in the unsaturated zone, but the mechanism for mass transport the mechanism for mass transport is dictated by either groundwater or vapor, and we know that groundwater movement rates are much faster and more efficient for conveying soluble components. So you'll see faster rates of degradation occur within saturated conditions, and that's illustrated by some of those graphs that I showed earlier. So I'm going to pull my presentation back up because I've got the option to do so. Let's see here. So see the nice tiger on the screen. And I'm going to go from current slide because I want to go back. Can you see the presentation on the screen, please?
We can. Thank you, Paul.
Sorry, I'm advancing back quite quickly. I apologize. So yeah, this one probably shows it quite a bit better, right? So if we just look at, you know, if we look at unsaturated conditions here in RDC 11 with benzene, we see a significant knockdown. But if we were to look at the percentage, you know, the relative degradation rate here, this is probably showing better degradation rates in saturated conditions. But we can see the TVPH when we're looking at that total mass fraction is a little bit retarded here because of how fast that material comes off of the unsaturated soil based on vapor movement, or call it downward migration of precipitation as it moves through after a rain event. But we look at the degradation rates, the comparative reduction between these two data points is more significant than here. Similarly, let's look how number 12 looks, right? So again, this is a fairly small move, but we get this very large move when looking. Again, we have bigger numbers here to work with, and probably good contact here as well. So you can see comparing these percentages, right, versus these percentages, you probably have a much larger reduction percentage comparison between looking at the benzene and at the TVPH within this zone as well. So, oh, sorry, my pointer's off. So I've been pointing this whole time and nobody can see my pointer. So talking about shallow conditions here, this percentage between these two data points versus these two data points, and then these two data points between these two data points, right? So you can see that space between here is not as big as the space between here. So we get more efficient rates of degradation in the saturated zone than in the unsaturated zone. So long-winded version of response, but that is the case.
Thank you, Paul. There's one more question from Hayley, and I just want to acknowledge Hayley is from Shell, but she's also the NICOLA chair of the organizing committee for the SUSTREM conference that's being hosted. Hayley asks, was there any physical LNAPL removal, or were all the reduction attributable to the application of BOS? Before you answer that, I am aware that we need to have a hard stop to be mindful of people's diaries in 3 minutes. So if you don't mind, if you could pop up your last slide again with your contact details so that people can just jot those down if they want to ask you questions, Paul. But then if you could answer the question, did you get it?
There we go. There's the final slide for you so that it's up on your screen. And yes, I've got the answer to the question. Very, very good question. So physical removal of NAPL did occur prior to implementation of anything that we were involved in. So prior to the RDC, prior to the first injection event, there was a mechanical system operating on the facility property that was capable of about 25,000 gallons of extraction per month. However, that system was terminated prior to us becoming involved in 2013. So all removal following the AST becoming involved has been strictly handled by the implementation of this technology.
Thank you. One more quick question. We could probably fit in one more.
Okay.
Going. Well, then I'd like to thank you and your colleagues. It's always never the individual. It's always people also, you know, beside you and behind you that's supporting you. And we'd like to thank you very, very much for the presentation. It was lovely. I just want to ask you, just please switch on your camera if you don't have a onesie on or something like that. Still, I know it's very early in the morning, that people can just see your face. And then colleagues, Then, colleagues, thank you very much for attending, and we'll be in touch soon with the next webinar.
Thank you, everyone.
Bye-bye.